Imagine that a ball rests on one side of a hill. Classical mechanics tells us that unless I kick this ball hard enough and give it enough kinetic energy to surmount the potential energy of the hill, it simply cannot travel to the other side. But what if I told you that in the quantum world, even if a particle doesn't have enough kinetic energy to pass through a barrier, sometimes it just ends up on the other side? This is called quantum tunneling. So how does this happen? Well, quantum physics is largely probabilistic. According to Heisenberg's uncertainty principle, it is impossible for us to know both the exact position and momentum of a particle. But we can represent a particle's position with probability, or something called a wave function, where the peaks of the wave represent the most likely positions of the particle. Now, let's imagine that probability waves are a lot like physical waves. We all know that light or electromagnetic waves can both reflect and refract. When an electromagnetic wave encounters a boundary at a certain angle, all of the light gets reflected without any refraction. This is known as total internal reflection. But what's really interesting is that Maxwell's equations tell us that not all of the light is actually reflected. Instead, a tiny, rapidly decaying wave known as an evanescent wave appears at the boundary. Similarly, when our particle, or the probability wave of that particle, encounters a boundary, it gets reflected, also forming an evanescent wave. Now watch this. If the barrier is thin enough, there is actually a chance that the evanescent wave doesn't completely decay before it reaches the other side. Remember that the probability wave of a particle represents the possible locations where that particle can be found. So if the evanescent wave of the probability wave makes it through the barrier, this means that there's a small but non-zero probability that our particle can be found on the other side of the wall. There's even a chance that you'll find the particle inside the wall itself. Let's take a look. Here's Schrodinger's equation. This is our wave function that represents the particle's position. If we do some math, we find that the probability of finding our particle inside the wall is given by this exponential decay function, which is not surprising because this represents our exponentially decaying evanescent wave. Again, since our probability wave represents the possible locations of our particle, there's a possibility that our particle can be found on the other side or even inside a barrier, thanks to quantum tunneling. Now, don't get your hopes up. We won't be walking through walls anytime soon because as the mass of an object increases, the probability of finding it on the other side of a barrier decreases. Which is why quantum tunneling is just one of the many classical wisdom-bending phenomena that occur on the subatomic level, or in video editing. Thanks for watching.